Welcome back. In this section, we're going to introduce the idea of inverse trigonometric functions. Now, of course, we do have a little bit of a problem when we're defining our inverse trigonometric functions, and that's that we know that inverse functions only exist when the function that we have is a one-to-one function. And if you're remembering how the graphs of our trig functions look, we know that they're not one-to-one. For example, the graph of sine of x clearly would fail the horizontal line test. The horizontal line would pass through it not just once, but actually infinitely many times. So sine is not one-to-one, and the same thing is also true for all of the other functions. This is not a surprise because all of our trig functions are periodic, which means that they repeat themselves, which means that they repeat the same y values over and over. So if you're looking at the graph of tangent, you know that it's just going to keep repeating itself again and again and again, which means that a horizontal line would pass through that graph in multiple places. Which means that technically we wouldn't be able to have an inverse of any of our trig functions over their entire domain. So that's the little trick that we're going to work here. We're going to restrict our domain so that instead of talking about, let's say, sine of x for all real numbers x, we're going to restrict that domain to just that part of the graph where sine is a one-to-one function, and then we'll be able to define our inverse. So the interval that we'll be working with for sine of x is the interval from negative pi over 2 to pi over 2. And the reason why we're working with that as our interval, if we're thinking about the graph of sine of x, we know that between negative pi over 2 and pi over 2, the graph of sine of x would look a little something like this. It would reach its maximum value of 1 at positive pi over 2, and it would reach its minimum value of negative 1 at negative pi over 2. And you can see here that this is very much a one-to-one function. Any horizontal line would pass through this graph in exactly one place. And so that's the idea here. We're going to restrict our domain for sine of x just to that little interval from pi over 2 negative to pi over 2 positive, including those endpoints. And since that's a one-to-one function, then we can define an inverse. And so the name for our inverse function is the inverse sine function, and we've got a couple of ways that we can write them. One is by writing this, y equals sine with a little minus 1x, and that little minus 1 means inverse, just like it did back when we were talking about inverse functions. Or, alternately, another name that you can give for the inverse sine function is the arc sine function, and you could write that as y equals arc sine of x. These both mean exactly the same thing. So you might see arc sine sometimes, you might see sine inverse sometimes, but they're both referring to exactly the same thing. They're both referring to the inverse of the sine function over that restricted domain. So, of course, things that we know about inverse functions come back here too. Inverse functions, they switch the inputs and the outputs. So you know, for example, with sine, you can think of that as the input being an angle and the output being the ratio of the side lengths of a right triangle, or you could think of the output as being y over r, or you could think of the output as being the y value on the unit circle, however you want to think about sine of x. But then for sine inverse, it will just switch those. It'll switch the inputs and the outputs so that instead of having an angle being the thing that's put into our function, an angle is what comes out of our function. And therefore, if you say that you know that sine of pi over 6 is a half, then sine inverse of a half should be pi over 6. Or similarly, you know that sine of pi over 4 is root 2 over 2 using your special triangle. So sine inverse of root 2 over 2 should be pi over 4. One thing I want to just draw our attention to, which is that we've restricted our domain to negative pi over 2 to pi over 2. In other words, we're going to be thinking about our angles as, again, only being measured in radians here. So throughout, whenever I'm talking about an angle, and if I'm thinking about an inverse trig function, I'm thinking about that angle being measured in radians. And that's throughout. That'll be for all of the inverse trig functions that we'll be looking at today. So, of course, other things that you know about inverse functions, they switch their domains and ranges. And so for the graph of sine, we had that the domain was just from negative pi over 2 to pi over 2. And we had the range was from negative 1 to 1. And so for the inverse sine function, they'll have the opposite of that. The domain will be the values from negative 1 to 1, and the range will be the values from negative pi over 2 to pi over 2. Also, again, notice that we're switching our points. So on the graph of sine of x, we had this point, which was pi over 2, 1. And on the graph of sine inverse, we have the same point, but with the coordinates switched. We have the point 1, pi over 2. Okay, so to evaluate our inverse sine function, we've got a couple of options. If the angle turns out to be something nice, then we can find the value of an inverse sine function just using our special triangles. Or if it turns out to be an angle that's a multiple of 90 degrees, we can do that in terms of thinking of the unit circle. Probably not a big surprise here. The more times you've evaluated sine x, the easier you'll find it to evaluate sine inverse. So for example, I'm looking at this sine inverse of a half, and I happen to know that there is a special triangle out there where I do get a value for a half for sine x, and that's our old friend, the 30, 60, 90 triangle. So pi over 6, pi over 3, and pi over 2, if we're thinking in terms of radians. And I know that for this triangle, if I'm looking at the pi over 6, the 30 degrees, sine of that would be opposite over adjacent. Sine of pi over 6 would be a half. So that means sine inverse of a half should be pi over 6. I'm not going to write that little second sentence down here at the bottom every time, but that's my reasoning for how I know that this is true. I know that since sine of pi over 6 is a half, then that means sine inverse of a half should be pi over 6. Sine inverse of negative 1, this again, we just have to ask ourselves, what angle are we at if sine has a value of negative 1? And if you're remembering your graph of your sine function, you know that sine has a value of negative 1 when x is negative pi over 2. And since we know that sine of negative pi over 2 is negative 1, then what's the angle that gives us a value of negative 1? The angle is negative pi over 2. So sine inverse of negative 1 is negative pi over 2. All right, next one up, arc sine of negative root 3 over 2. So again, arc sine and sine inverse, they both mean the same thing. It's the inverse function of the sine function. I know that I'm looking for the output of my sine function to be negative, and if you're remembering, we said that we were defining sine on the domain from negative pi over 2 to positive pi over 2, just in that little interval that we've got there. Now, in quadrant 1, you know that sine would give you a positive value, and so whatever our angle is, it's certainly not in quadrant 1. We know our angle then has to be in quadrant 4. It needs to be somewhere between negative pi over 2 and 0 radians. So now what am I going to do? I'm going to start off by first thinking about where do I get a value for sine of root 3 over 2. And if you're going back again to that special triangle we had on the previous slide, for sine, you know that root 3 over 2 would be the output if your angle was pi over 3. Sine of pi over 3 would be opposite over hypotenuse, or root 3 over 2. So we know that sine of pi over 3 is positive root 3 over 2, but then that means if pi over 3 gives you that angle of gives you that output of positive root 3 over 2, then if you had a reference angle of pi over 3 in quadrant 4, where sine is negative, that should have an output of negative root 3 over 2. So that if you looked at sine of negative pi over 3, that is negative root 3 over 2. And now we know that, we can then answer our question. Since we know that sine of negative pi over 3 is negative root 3 over 2, then sine inverse of negative root 3 over 2 is negative pi over 3. So again, a lot of this really depends on us knowing our sine and our cosine and our tangent, those basic functions, knowing them very well. So again, spoiler here, we're talking about inverse sine right now, but we will be very soon talking about inverse cosine and inverse tangent. So a lot of the things that I'm saying now really apply in all of these situations. And so for all of them to be able to evaluate those inverse trig functions, we really need to already know very well our basic trig functions. Sometimes we'll need to find approximate values of our inverse trig functions. So I'm going to explain finding inverse of sine, but finding the inverse of cosine or tangent is done in much the same way. So you'll notice here that above the sine button that we have the inverse sine function, sine inverse, right there in small orange print. And so if you want that function, it's just as simple as touching second function and then your sine button, and that will give you inverse sine. So if you wanted to find something like sine inverse of 0.2, you would just have to enter second function sine inverse 0.2 and then hit equals. Now, one thing you do have to be careful here is that, remember, we want our output for these inverse trig functions to be given in radians. So you will have to make sure that your calculator is in radians mode. If it's not, then you'll want to put it in radians mode by touching the DRG button. So that's something that we'll have to do for finding approximate values only. For exact values, like I said, for those, we'll be thinking in terms of the graph of our trig function. We'll be thinking in terms of the special triangles. We'll be thinking about those to find our values of inverse sine, inverse cos, inverse tangent. But in those cases where the value that we're looking for doesn't come from a special triangle, then we will need to use our calculator. So, for example, here we want to find the approximate value of inverse sine of 7/10. And so we know then definitely we're not going to be using our special triangles here. I mean, it tells us that we want the approximate value, but if you've done enough work with your trig functions, you'll know that 7/10 is not one of the numbers that comes out of any of your special triangles. So we won't really be able to find the exact value of sine inverse of 7/10 anyway. The best we would be able to do is find the approximate value. And if we use our calculator, second function, sine, and then enter in 7/10, we get that this is approximately 0.775397, so about 0.775, and that is radians. So this is not 0.775 degrees, this is 0.775 radians. Now, if you're thinking about doing compositions of trig functions, this is something where we have something nice from the past. Remember that when you compose a function with its inverse, that they undo each other. And that's true when it's F inverse composed with F. It's also true when it's F composed with F inverse, as long as the value that we're putting in is a value that's inside that domain. So if x is, for example, between negative pi over 2 and pi over 2, so if it's in our domain for sine of x, then sine inverse and sine will cancel each other out. And similarly, if x is in the domain of sine inverse, if it's between negative 1 and 1, then sine composed with sine inverse will cancel each other out. So some of these problems are going to be fairly quick to do. For example, if we're looking at sine composed with sine inverse of 0.2, remember that the domain for sine inverse was all the values from negative 1 to 1, and 0.2 definitely is inside that interval. So sine composed with sine inverse, they will undo each other, and you'll be left with just 0.2. And similarly for the next one, the restricted domain for sine, that was from negative pi over 2 to pi over 2, and pi over 6 is definitely inside that interval. So this is a value inside the domain, which means sine inverse and sine should undo each other, and you should just be left with pi over 6. Now, of course, there are going to be some complications. One is an easy complication to deal with, and that's if you had a value of x that was not in the domain of sine inverse. So if you had an x that was larger than 1 or less than negative 1, then automatically you know that sine inverse would be undefined. And that's because if you were saying what is sine inverse of 2, for example, you'd be asking what's the angle that gives you an output value of sine that is 2, and the answer is there isn't an angle, because we know the value for sine is always between positive 1 and negative 1. So since you would have a value of sine inverse being undefined, then anything composed with sine inverse would have to be undefined. So if we know, for example, that sine inverse of 2 is undefined, then so would be sine composed with sine inverse of 2. That would also be undefined. Now, we do run into a little bit of a plot twist here. If we're talking about a value of x that's not inside the restricted domain of sine, remember that for sine x, the restricted domain was values between negative pi over 2 and pi over 2. But that doesn't mean that you couldn't put other values of x into this function. So you could figure out, for example, what is sine of pi, or what is sine of 7 pi over 4, or any other value. The problem comes in when we're looking at composing sine inverse with sine, because although you can put numbers in for x that are outside of that interval, sine inverse is only going to give you values that are inside that interval. So, for example, you know that sine of 3 pi over 2 is negative 1. That for sure is something that's true, and you can confirm that by looking at the graph of your trig functions and reminding yourself that at 3 pi over 2, the graph of sine has a y value of negative 1. But if we looked at sine inverse of sine of 3 pi over 2, we would be wrong if we thought that the sine and the sine inverse canceled each other out and we'd be left with 3 pi over 2. That's actually not the case, and the reason for that is sine inverse only has as its output values between negative pi over 2 and pi over 2. So sine inverse is not going to give you 3 pi over 2 as the output. It's going to give you as the output an angle that would also be equivalent to sine of 3 pi over 2. So we know that sine of 3 pi over 2 is negative 1, but 3 pi over 2 is not a value in this interval. We know that negative pi over 2 is a value in that interval and does also have a value of negative 1. So if you were to look at composing sine inverse with sine of 3 pi over 2, since sine inverse can't give you 3 pi over 2 as an output, it will give you as an output an angle that gives you the same value that sine of 3 pi over 2 would have, which happens to be negative pi over 2. So the reason here why we're getting a different angle as our output is because sine inverse can't give you 3 pi over 2 as the output. It has to give you something between negative pi over 2 and positive pi over 2. And the angle that has the same value for sine as 3 pi over 2 is negative pi over 2. And that's why that's our output. Now, we're going to do a bunch of examples of these. So some of these will be fairly fast, and some will take a little bit more effort. All right, the first one is one that's actually relatively short. So we're looking at sine composed with sine inverse of 1.3, and I can say that sine inverse of 1.3 is undefined. And I know that it's undefined because remember the domain for sine inverse was just the values from negative 1 to 1. So sine inverse of 1.3, that's not inside the domain, so sine inverse of 1.3 is undefined. And if sine inverse of 1.3 is undefined, then anything composed with it is also undefined. So my answer here, sine composed with sine inverse of 1.3, is also undefined. Okay, for the next two, these are both examples of something where we could figure out if we felt like it, what is sine of 9 pi over 10 or 15 pi over 13. But the one thing that we know for both of these is that these are angles that are not in our restricted domain. Remember that our restricted domain for sine was from negative pi over 2 to pi over 2. And we'll see that both of these angles happen to not be in that interval. So remember, the idea here is that whatever we're going to get as our output is going to be an angle that is in that interval from negative pi over 2 to pi over 2. And whatever that angle happens to be, it has to give us exactly the same value that sine of 9 pi over 10 would be. So really, that's kind of what we're looking for here. We're asking ourselves, what is the angle that's in that interval from negative pi over 2 to pi over 2 that would give us the same value for sine as sine of 9 pi over 10. So let's figure this out. Let's first start out by figuring out where is 9 pi over 10. And if you were to figure this out, you'd find that 9 pi over 10 happens to be in quadrant 2. And you know that because, of course, pi radians, or 180 degrees, is the same thing as 10 pi over 10, or pi. So that means 9 pi over 10 is a little bit above that negative side of the x-axis. And that also tells me that my reference angle should be pi over 10. So the one thing that we know here, if we're thinking about quadrants, we know that we're in a quadrant where sine is positive. And the quadrant where sine is positive between negative pi over 2 and pi over 2 would be quadrant 1. Remember that sine inverse is only going to give us angles that are in quadrant 1 or quadrant 4. That's the reason why we're not going to get 9 pi over 10 as our output, because 9 pi over 10 is not in that interval. So now we need to ask ourselves, well, what's the angle that is in quadrant 1 or quadrant 4 that does give me the same output as sine of 9 pi over 10? And we know that it should be then just pi over 10. Sine of pi over 10 and sine of 9 pi over 10, those would both be positive because those angles are both in quadrants where sine is positive. So I can say here, just as a little note to myself, since sine of 9 pi over 10 and sine of pi over 10 are equal to each other, then you know that sine inverse of sine 9 pi over 10 would be pi over 10. That's why we're getting pi over 10 as our output, because pi over 10 is the angle that's in that interval from negative pi over 2 to pi over 2, where sine has the same value as sine of 9 pi over 10. And we'll do the same sort of thing here for sine inverse of sine of 15 pi over 13. We'll have to first figure out where is 15 pi over 13, and we'll just do a little drawing here. 13 pi over 13, that would be the negative x-axis. So 15 pi over 13, that's somewhere in quadrant 3. And so the reference angle then is 2 pi over 13. Now, again, we know who's positive in which quadrant, and we're in quadrant 3, where sine happens to be negative. So we're going to get for our output, it has to be something where sine is negative. And again, sine inverse is only going to give us output in quadrant 1 or quadrant 4. It couldn't be quadrant 1 because that's where sine is positive. So it means we must be quadrant 4 for our output. And so if we're thinking about this, if you're thinking about what would be the angle, you know that negative 2 pi over 13, that's an angle that's in quadrant 4. It has the same reference angle as 15 pi over 13, and sine is definitely negative in quadrant 4. So you know then that sine inverse of sine of 15 pi over 13 should be negative 2 pi over 13. And the reason for that, of course, was because since sine of 15 pi over 13 is equal to sine of negative 2 pi over 13. And that angle, negative 2 pi over 13, is in that interval from negative pi over 2 to pi over 2.